Hello everyone, my name is Amirpooya Shirazi. I'm a first year PhD student doing research under Dr. Aladdin Alwisy's supervision within the Smart IDC lab. And today I'm going to present one of our research studies titled as Enhancing Robotic Path Planning in Industrialized Construction, a Novel Benchmarking Approach. As the agenda of this presentation, I will start with a brief introduction discussing the importance of this study, then describing the current limitations and come up with the research question as well as the study's objective. Furthermore, I'll continue with the overview of the framework followed by a case study tested on a simulated timber structure assembly task. And lastly, the outcome of the presented framework will be discussed. Within the last decade, several studies utilized robotics to bring automation within the construction industry in order to eliminate the limitations within the time and cost efficiency as well as safety aspects. For instance, UAVs and UGVs have gained popularity within inspection and executive tasks such as material delivery or installation. Additionally, industrial level robotic arms gain attraction due to their mobility and precision within construction assembly tasks such as additive manufacturing. Within the domain of modular construction, early advancements such as off-site modular construction, considered as manually and CNC machine-based construction, have shifted towards the integration of those robotic arms to tackle the need of diversity required within designs. However, utilizing such robotic entities within the off-site modular construction sector has brought several challenges, slowing construction researchers to investigate this area. Among those challenges, a fundamental issue is to choose a suitable inverse kinematic path planner algorithm to let those robots carry construction components, such as studs within different lengths and orientations, in a safe, efficient, and applicable context. Briefly describing, an inverse kinematic path planner algorithm utilizes the goalpost, which is the robotic end effector's target position and orientation, and the current robot state includes the joint angles of the robot to calculate the path that the robotic arm needs to follow, called as trajectory basically, to reach the target post while avoiding the environment's obstacles. On the right-hand side, you can see a simple visualization of how inverse kinematic works upon giving the target coordinate pose to the robot, basically. As you can see, this slide provides a simple demonstration of a robotic arm pick-and-place task being done by two different inverse kinematics path planner algorithms called Kurobo on the right-hand side and RRT Connect on the left-hand side. The difference between the trajectory being measured by those path planners rise up a certain need to identify what metrics are important within a certain construction assembly task in order to identify the best or the well-suited inverse kinematic path planner for that. By knowing those metrics, it will be more straightforward to choose that best IK planner basically upon designing certain assembly tasks utilizing those robots. As a result, the research question here in this study would be what metrics are required to get measured in order to propose a meaningful comparison between different inverse kinematics path planner pipelines within a certain construction assembly task. And to answer this, the objective of this study is to establish a benchmarking framework to determine the most sensitive metrics among a set of extracted metrics out of the literature review while deciding on the selection of an inverse kinematic planner for a certain assembly task. So the proposing framework contains three phases. The first phase is to identify the metrics within previous IK benchmarking studies. After gathering a database of commonly used metrics, and a standardized table of metrics can be designed by filtering out those with a criteria that depicts the importance in construction industry, such as is the metric is required to plan a safe or fast or real time or maybe efficient movement or not. Within the second phase, the design assembly should be divided into smaller subtasks that are representatives of steps being done to do the whole assembly. By filtering out the subtasks that are not demonstrating a scenario type that has addressed within previous benchmarking studies, and it can address some testing gaps, a set of testing subtasks or scenarios can be gathered. So this will let us evaluate or uh, or maybe we rank the metrics by measuring them between two or more IK planner results within certain scenarios individually. Lastly, since we have already seen the result of testing IK planners on a given scenario, comparing the measured metrics will give us insight on the importance of those rankings. So ranking the importance of those metrics will result in a pre-ranked metric table that can be used to compare different IK planners in other scenarios, including the same feature. To test the framework, we have created a case study on the Smart IDC Lab simulated environment, including two ABB 6620 robotic arms with multifunctional end effectors capable of picking, placing studs, OSB sheeting plates, and nailing in different orientations. And additionally, two different conveyor belts actually were designed to move the assembling structure in order to let the robots reach different parts of the wall. So, to create the standardized table of evaluation metrics, we have explored more than 20 technical researchers that benchmarked their IK planners to the previously known planners. As a result, six major metrics were identified that are success rate, planning time, path length, path smoothness, path clearance, and end effectors error. Among those metrics, most of the planner pipelines have parameterized path clearance and end effectors as their inputs. Therefore, by excluding those metrics, we have considered success rate, planning time, path length, path smoothness, and finally, minimum angle, which is a function of path smoothness, as our standard metrics table, basically. Within our assembly scenario, a timber wall was being assembled containing different parts that have been categorized into horizontal, vertical, stud, as well as OSB sheeting plate. Therefore, four tasks of picking and placing of studs, vertical and horizontal studs, picking and placing of OSB sheeting plates, and also nailing studs and OSB sheeting plates have been selected as the testing scenarios. So to validate the pipeline, the scenario of picking and placing a top plate, which is a 12 feet horizontal stud, has been selected as the representative of the first task, basically. By running Kurobo and RT Connect as our two comparing IK algorithms, we have realized that Kurobo, which is being shown on the right hand side, was generating a more reasonable trajectory. By measuring the metrics, we have realized that although both planners got 100% success rate upon repeating the same task for 10 times, the planning time for Kurobo was longer, meaning that it took more time to generate a path, but much faster to execute a path if you compared the videos or the outcomes. The matter of executing a trajectory is also laid under the path length. Although we expected a smoother trajectory being calculated by Kurobo, the smoothness metric, which is the average angle between each three sequential positions of the robot's gripper center point, was less compared to RRT Connect, meaning that although Kurobo shown a better result, the generated path seems to be sharper. To make sure that the sharpness of the generated trajectory is right, like the comparison, we decided to add a minimum angle metric, which is the minimum number among the values being averaged in the path smoothness. This metric is just considered as a proving metric that the path smoothness does not have importance among the metrics need to be considered for testing such scenarios. As a result, success rate which is a mandatory metric, as well as the path length, were considered among most important metrics need to be measured for selecting the best IK planner algorithm for such scenarios. On the other hand, path length and path planning time were not that important in this context. Finally, this research successfully demonstrated our weighted validation framework's ability to evaluate the path planning algorithms under the challenging conditions such as dimensional asymmetry, which is typical in construction robotics. While validating through a single robotic workstation scenario, the framework's design enables extension across diverse workstations and manufacturing strategies throughout the industrialized construction sector. Finally, our future research will focus on categorizing various IC manufacturing strategies to build comprehensive task datasets, leading to a standardized rule-based methodology that can guide robotic operations across the entire construction industry. Finally, thanks for your time and attention, and I would also be happy to answer any questions regarding this research. Thanks.